Have you ever really stopped to think about what keeps your favorite apps and websites from just collapsing? There's this silent, invisible guardian working behind the scenes, a thing called a rate limiter. Today, we're going to pull back the curtain and see exactly how they work, diving right into Chapter 4 of Alex Su's fantastic book on system design.
Seriously, think about it. Every single post, every message, every login, that's a request hitting a server. So what happens when millions of people, or hey, even just one nasty bot, try to do that all at once? What's the defense? Well, you guessed it, it's a well-designed rate limiter.
A rate limiter is basically a gatekeeper. When this massive flood of requests comes pouring in, it lets a reasonable number through and just says nope to the rest. And it does that by sending back this very specific error code, 429. It's pretty much the digital version of a bouncer at a club saying, sorry, we're full, try again later. But why is that gatekeeper so important? I mean, can't we just build servers that can handle anything we throw at them? Well, not really. Let's break down exactly why this isn't just some nice-to-have feature, but an absolute must-have for any service that wants to stay online. Okay, so there are three huge reasons. First up is security. This is your main line of defense against what are called denial-of-service attacks, where someone just tries to drown your system in traffic. Second, it's about the money. Fewer junk requests means you need fewer servers, and that saves you cold, hard cash on your cloud bill. And finally, and maybe most importantly, it's about stability. Rate limiting makes sure the whole system stays up and running for all the legitimate users, preventing a catastrophic crash.
So we're sold. We need one. The very next question is, where do we actually build this thing? The placement of your rate limiter is the first huge architectural choice you have to make, and it has some really big consequences for how secure and reliable your system is.
You've basically got two choices. Put it on the client, so inside the user's web browser or their mobile app, or put it on your server. And honestly, the client is just not the place for it. It's totally unreliable. A clever user can just turn it off or fake it. The only place where you have full control, where it's secure, where it's authoritative, is on the server side. It's really the only way to go for any serious system.
Now, even once you've decided on the server side, you still have options. You could, for instance, bake the rate-limiting logic right into your application servers, like you see on the left. But a much more common and scalable way to do it, which you can see on the right, is to pull it out into its own separate layer, like a middleware or what's called an API gateway. This keeps things clean and lets that one piece of tech handle traffic for lots of different services at once.
All right, so we know where to put it. Now we get to the really fun stuff. How does it actually work? How does it decide who gets in and who gets blocked? This all comes down to the algorithm, the brain, the core logic that's powering this whole operation.
Let's kick things off with an industry heavyweight, the token bucket algorithm. This one is super popular, and for good reason. It's incredibly flexible and powerful. We're talking big names here, like Amazon and Stripe, who rely on this exact method to manage their massive API traffic.
The way this works is actually pretty simple to picture. Imagine a bucket, and into this bucket we're dropping tokens at a nice steady pace, let's say 10 tokens every second. Now, every single request that comes in needs to grab one token from the bucket to pass. So if a sudden burst of 50 requests shows up and there are 50 tokens in the bucket, great, they all get through. But if that bucket is empty, sorry, you're not getting in until more tokens get added.
So, the huge advantage here is that it can handle these sudden bursts of traffic, which, let's be honest, is how the real world works. It's also pretty efficient on memory. The downside? It can be a little tricky to tune. You have to decide on the bucket size, like how big of a burst do you want to allow, and the refill rate. Getting that balance just right is a bit of an art.
Now, for contrast, let's look at a much simpler algorithm, the fixed window counter. The idea here is dead simple. You just count how many requests show up in a set period of time, like, say, 100 requests per minute. As soon as you hit 100, you just block everything else until the next minute ticks over. Sounds easy, right? Well, it has a massive flaw, and this diagram shows that flaw perfectly. Let's say your limit is 10 requests per minute. Well, what if a user sends 10 requests in the last 30 seconds of 1 minute and then sends another 10 requests in the first 30 seconds of the very next minute? Uh-oh, they just sent 20 requests in a 60-second span. That's double your limit. This problem at the edge of the windows can totally defeat the purpose of your rate limiter.
So these algorithms sound great on a single computer, but modern web services don't run on one computer. They run on hundreds, maybe thousands of them, all over the world. So how in the world do you keep a consistent count when a user's request could be hitting any one of those servers? This is the real challenge, making it work at scale.
And here's the key takeaway.
You absolutely cannot store the counter on the rate limiter servers themselves. If you did, each server would have its own separate count, and the limit would be basically useless. The solution is to have a centralized, super-fast database that all the rate limiters can talk to. And the industry standard for this job is an amazing piece of tech called Redis.
Okay, so let's walk through the life of a single request. Here's the play-by-play. The request comes in and hits the limiter. The limiter immediately shoots a question over to Redis. Hey, what's the count for this user? Redis shoots the answer back. The limiter checks if there's room. If yes, it tells Redis to add 1 to the count and then passes the request along to the main application. If the limit's already been hit, bam, rejected on the spot. It all happens in milliseconds.
And here you have it, the whole shebang, the complete architectural blueprint. You can see the user's request coming in from the left. It hits our rate limiter middleware. That middleware checks the rules, and then it checks the counter in our central Redis store. And from there, it's a simple fork in the road. Either the request gets the green light and moves on to the API servers, or it gets the rate-limited response and is sent right back where it came from.
So what's it actually like for the person or the application that gets blocked? How do they know what the rules are, and how do they know when they've broken them? Well, a well-designed system needs to communicate all of this really clearly.
The first and most important signal is the HTTP status code. When your request gets blocked, you don't just get some vague error. You get this number right here, 429. For any developer out there, that code is an unmistakable signal. It means one thing and one thing only: too many requests.
But a truly great system does more than just say no. It gives you helpful information using what are called HTTP headers. With every single response, it can tell you what the total limit is, how many requests you have left to use, and, this part is crucial, if you are blocked, it'll tell you exactly how many seconds you need to wait before you try again. This allows other programs to be smart and respectful of the limits.
And this quote really just nails it. A rate limiter isn't something you just set up once and then walk away from. It's a living, breathing part of your system. If you make the rules too strict, you're going to end up blocking legitimate users and making them angry. But if the rules are too loose, you risk the whole system going down. You have to be constantly monitoring and tweaking to find that perfect sweet spot.
So in the end, you can think of a rate limiter as your system's immune response. Its job is to protect the health of the whole by spotting and rejecting threats. But that's a really tough design challenge, isn't it? How would you build one that's strict enough to keep everything stable, but also fair enough that it doesn't punish your best and most active users? That right there is the million-dollar question in system design.